Good morning, children. Today we are starting the new chapter, periodic table. So before directly going into that chapter, I would like to ask you some questions. I hope that all of you have gone for shopping, isn't it? So when you go for a shopping, there will be a person who will be standing at the door and they will be asking you, what do you want to buy? Sometimes we will be saying churidar, sometimes we will be saying sari or frock or something. So they will say, okay, you go to this floor, second floor or third floor, we will directly go there. And when you go there will be different people who are dealing with different things, isn't it? One person will be dealing with sari, the other one will be dealing with the other accessories and all. And have you ever seen anything messed up in between, like the blouse materials together with the sari or sari together with the churidar materials? Have you ever seen such things? No, because they are perfectly arranged, isn't it? That's why when we ask them to give us a color, or give us a sari or give us a material of that kind, they will directly go and pick that. Why? Because they are perfectly arranged, isn't it? The second example what I have to tell you is that I hope that you people have gone to libraries, isn't it? So if you go to a library, have you seen all the books scattered on the table? Never, isn't it? You have never seen that. These books are perfectly arranged. How they are arranged? Fiction is on one shelf, comics will be on another shelf, then science related magazines will be in another shelf. And those science related magazines itself, they will be arranged according to the volume, like volume 1, 2, 3, etc. And comics also, if you go there, it will be arranged according to the alphabetical order, isn't it? So things are always perfectly arranged. It's very easy for us to pick them up when they are perfectly arranged. So here we are going to study about the chapter where we are studying about the arrangement of elements, perfect arrangement of elements. So before going directly deeper into that chapter, I have to tell you a few things about it. So the first scientist who tried to give a arrangement of elements was Lavoisier. This name is familiar to you, isn't it? Lavoisier. He tried to arrange the elements, metals and non-metals. Okay, he tried to arrange the elements in the form of metals and non-metals. But when he tried to arrange the elements according to this pattern, there was a limitation. He was not able to arrange the metalloids who showed both the properties. He didn't know where to keep these elements. When he arranged the elements only on the basis of metals and non-metals, he was not able to arrange metalloids. He did not know where to keep it. So his arrangement was discarded. After that came another scientist. Don't say scientist, chemist you can say. He was Dobereiner. Okay, Dobereiner. His law of classification was known as law of triads. Okay, triads. Tri means 3, isn't it? Tri means 3. So these all scientists, these all chemists or scientists, they tried to arrange the elements according to their atomic mass. Okay, so that you should keep in mind. All these people tried to arrange the elements according to the atomic mass. So his classification was that if you are arranging the elements, okay, you are arranging the elements, when you take the arithmetic mean of the first and the third element, arithmetic means average, of the first and the third element, that will give you the atomic mass of the second element. Okay, so what was his classification? If you take the arithmetic mean of the first and the third element, that will give you the atomic mass of the middle element. For example, I am taking lithium, sodium and potassium. atomic mass 7, here 39. Okay, so according to his law, according to his method, I am going to find out the atomic mass of sodium. So what he said was that if you take the arithmetic mean of the first and the third element, okay, arithmetic mean of the first and the third element, that will give you the atomic mass of sodium. So here it is 46. 46 divided by 2, that is 23. So you know that atomic mass of sodium is 23. So that was a perfect arrangement, isn't it? But it was not. He could arrange elements only according to a maximum of 20 or 20 elements. He was able to do this arrangement only up to elements, up to 40. After that, he could not arrange because when he took the arithmetic mean, he did not get the arithmetic atomic mass of the middle element. And because of that, that property or that arrangement, the law of triads, was also discarded. Then came another chemist. His name was John Newlands. John Newlands. Okay. Okay. So his arrangement was known as law of octaves. Okay. Law of octaves. Octa means 8, isn't it? So what he told was that if you are arranging the elements in the increasing order of the atomic mass, okay, when you are arranging the elements according to the atomic mass, the first element and the 8th element will be having the same property. It is a repetition of the first element. Every 8th element will be the repetition of the first element. Like the notes of music, you know, sa, re, ga, ma, pa, dha, ni, sa, right? So 1, 2, 3, 4, 5, 6, 7, 8. See, like this. The first and the 8th element will be having the same property. It will be the repetition of the, every 8th element will be the repetition of the first element. So it was arranged by like the notes of music. Okay, and this theory was known as law of octaves by John Newlands. But when higher elements with higher atomic mass was discovered, this arrangement was not practically possible. So the law of octaves, which was put forward by John Newlands, was also discarded. After that came, after long years, came another Russian chemist, Dmitry Mendeleev. Actually, he was a person who tried to give a perfect arrangement for the periodic elements. So about Mendeleev and his classification and his advantages, we will be discussing in the next class. Thank you all of you. Have a nice day.
Imagine how difficult it would be for a teacher if she had students of 5 different age groups in the same class. Trying to teach different subjects and handle different levels of complexity for each student would result in a lot of confusion. Students in a school are allocated to classes based on the age group they belong to. It is because students in a class are likely to have similar attributes in terms of the level of knowledge, capabilities, height, and weight. Similarly, there are over 100 elements known to us. Scientists felt the need to classify them on the basis of some common properties. In this lesson, we will learn how the attempts to classify elements led to the evolution of the periodic classification of elements. At the end of this lesson, you will be able to examine early attempts at classification, analyze Daubernier's law of triads and Newlands' law of octaves, compare the merits and demerits of the law of triads and the law of octaves, list the main features of Mendeleev's periodic table and analyze the merits and demerits of Mendeleev's periodic table. The earliest classification categorized elements into metals and non-metals. However, this classification served only limited purpose because of the following reasons. The classification was at a very broad level. A large number of elements were classified as metals. However, they did not necessarily display similar chemical properties. For example, sodium and copper were both characterized as metals, but their chemical properties are very different. Some elements such as boron exhibited the properties of both metals as well as non-metals. It was difficult to determine how to classify such elements. After further research, a German scientist, Daubernier, arrived at a hypothesis in the year 1829. According to Daubernier, all elements occurred in groups of 3 when arranged in increasing order of atomic masses. He referred to these groups as triads. Daubernier's law of triads states that the atomic mass of the middle element of a triad is the arithmetic mean of the atomic masses of the other 2 elements. To illustrate this law, consider the triad of lithium, sodium, and potassium. The atomic mass of lithium is 7, the atomic mass of sodium is 23, and the atomic mass of potassium is 39. The arithmetic mean of the atomic masses of lithium and potassium is 23. This is equal to the atomic mass of sodium. Similarly, in the triad of chlorine, bromine, and iodine, the arithmetic mean of the atomic masses of chlorine and iodine is approximately equal to the atomic mass of bromine. While this law worked for some elements, it was not a success because all the known elements could not be arranged in the form of triads. The law did not hold good for elements with very low or very high atomic mass. For example, the arithmetic mean of the atomic masses of fluorine, 19, and bromine, 80, which comes to 49.5, varies significantly from the atomic mass of chlorine, which is 35.5. Since Daubernier's law could not successfully group elements, the attempts at classification continued. The next attempt came in 1864 when an English chemist, John Newlands, stated his observations in the form of Newlands' law of octaves. Newlands noted that when elements are arranged in increasing order of their atomic weights, the property of every 8th element is similar to that of the first element, similar to the first and the 8th notes in the musical scale. Consider the list of elements with their atomic weights in increasing order. Starting with lithium, the 8th element from lithium is sodium. Similarly, the 8th element from sodium is potassium. Lithium, sodium, and potassium show similar properties. For example, they are metallic in nature, have high reactivity, and conduct heat and electricity. Similarly, beryllium, magnesium, and calcium show similar properties. For instance, all the 3 elements are shiny and fairly soft. However, Newlands' law of octaves failed because it was not valid for elements of atomic masses higher than calcium. Newly discovered elements could not find a place in Newlands' table.